Now we will be discussing about the Carnot theorem and how does the explanation of Carnot's engine leads to the absolute scale of temperature. To begin with, we should be aware that this theorem consists of two parts. The first part is the main statement of the theorem, and the second part is sometimes called as the corollary of the theorem. The first part states that no engine can be more efficient. No engine can be more efficient than a perfectly reversible engine working between the same two temperatures. That is, if we consider a source at temperature T1 and a sink at some lower temperature T2, and then if we have an engine which is a reversible engine and it has got some efficiency eta, and now we imagine another engine, say R dash, some new engine with efficiency eta dash, working between the same two temperatures T1 and T2 as that of the previous engine, then this theorem states that eta dash has to be less than eta. At the most it can be equal to eta. So eta dash cannot be greater than eta. So we cannot imagine any other engine working between the same two temperatures T1 and T2 which is having an efficiency greater than this reversible engine working between the same two temperatures. Now we are going to prove this first part, but before that let us also see what does the corollary state. It states that the efficiency of all reversible engines working between the same two temperatures T1 and T2 is the same. So this is an extension of the original statement. It states that efficiency of all the reversible engines working between the same two temperatures T1 and T2 is the same, and it doesn't matter so whatever may be the working substance, so it does not matter what working substance we choose in order to perform the work. Of course, all these ideas are perfectly theoretical and they are applicable to reversible engines. So in order to prove this theorem, again we will use the same strategy of negation as was used in order to discuss the equivalence of Kelvin-Planck statement and Clausius statement of second law of thermodynamics. So let us consider a source of infinite heat capacity at T1 and a sink of infinite heat capacity at temperature T2 such that T1 is larger than T2. Now consider a reversible engine, say R, which extracts heat Q1 from the source, rejects heat Q2 to the sink, and performs a work W. This is a typical Carnot engine working between T1 and T2. Now consider another engine which is an irreversible engine I working between the same two temperatures, and suppose it extracts heat Q1 dash and rejects heat Q2 dash but performs the same amount of work W as that of the reversible engine. Now we are going to assume the converse of this statement, that is the efficiency eta dash of this engine when compared with the efficiency eta of the reversible engine. We are going to assume that eta dash is greater than eta. So this is in contradiction with the statement, and that's what we are going to prove. So if we assume that eta dash is greater than eta, we remember from the definition of efficiency that eta is just the work done divided by heat absorbed. So W by Q1 is greater than W by Q1 dash. Since work done is the same, this also means that Q1, excuse me, there is a slight correction. This dash should appear here. Eta dash is W by Q1 dash and eta is W by Q1. So this means that Q1 has to be greater than Q1 dash. So this is the first statement, that Q1 is greater than Q1 dash. Now if we remember, by the second law we have Q1 equal to Q2 plus W and Q1 dash equal to Q2 dash plus W. So this means that if Q1 is greater than Q1 dash, obviously Q2 has to be greater than Q2 dash. So these are the two important equations which we are going to use later. Now what we are going to do is we are going to couple the two engines. Since this engine is reversible, we can change or reverse its order of operation. That is, instead of extracting heat Q1 from the source and rejecting heat Q2 to the sink, it extracts now heat Q2 from the sink and rejects heat Q1 to the source. But by the second law, it requires an external agency to supply the work W in order to carry out this process. Now we can claim that this work W is to be provided, or it can be provided by this irreversible engine because it is performing work W. So just join this irreversible engine to the reversible engine by keeping all other quantities unchanged. So Q1 dash and Q2 dash. Now if we see at this composite system, we observe that net heat entering the source is upward arrow Q1 minus downward arrow Q1 dash. And since Q1 is greater than Q1 dash, this quantity is going to be positive. Similarly, for the sink, we can see that net heat Q2 is upward arrow Q2 minus Q2 dash is downward arrow Q2 dash. Again, since Q2 is greater than Q2 dash, this is going to be positive, and this is net heat lost. So we see that a net amount of heat is lost by the sink, which is at a lower temperature, and net amount of heat is gained by the source, which is at the higher temperature. So effectively there is a transfer of heat from sink at lower temperature to the source at higher temperature by this composite engine without any help from external agency. And this is not possible because it is in contradiction to the second law. So this process cannot happen. And since this process cannot happen, our initial claim that eta dash is greater than eta is incorrect. So yes, no other engine can be more efficient than the reversible Carnot engine. And this is how we prove the first statement or the first part of the Carnot's theorem. Now let us move to the corollary part or the second part of the theorem. Again, in this case, we are going to consider two reversible engines and going to prove that their efficiencies are going to be same. So there are two reversible engines with, and we are going to assume initially that their efficiencies are not same. So what we are going to assume is two reversible engines with unequal efficiency, and this claim we are going to prove it wrong. So it will mean that the two engines will be of same efficiency. So let us begin the discussion by assuming two reversible engines R1 and R2. One of them extracts heat Q1, rejects heat Q2, performs work W. The other extracts heat Q1 dash, rejects heat Q2 dash and performs work W. The same amount of work W. Now the efficiency eta 1 of this first engine will be W by Q1, and efficiency eta 2 of this second engine will be W by Q2. Sorry, W by Q1 dash. Right. And let eta 2 is greater than eta 1. So this will mean that W by Q2, W by Q1 dash is greater than W by Q1. This will also imply that Q1 is greater than Q1 dash since the work done are same. Okay. This can also imply, as we have already proved, that Q2 is greater than Q2 dash. Right? This we have already discussed in the first part. Now, since this engine is reversible, both of these engines are reversible, let us reverse the engine R2 and connect it to the engine R1 to create a composite engine. In that case, we will have R2 supplying the necessary work W, R1, anyway, it is fine. So this extracts heat Q1 dash, Q2 dash. Oh, the other way, we should write it the other way. So this is at T1, this is at T2. We have R1, Q1, Q2, W, and R2 is reversed. So it takes the work W, extracts heat Q2 dash, rejects heat Q1 dash to the sink. Yes, since R2 is reversed, this is the composite engine. Now again we look that the net heat gained by the source is Q1 minus Q1 dash, which is positive since Q1 is larger than Q1 dash, and net heat loss by the sink is Q2 minus Q2 dash, which is again positive. So yes, again what is happening is that heat is transferred from a region of lower temperature to a region of higher temperature, which is not acceptable. And since it is not acceptable, our initial argument that eta 2 is greater than eta 1 is not correct. So if eta 2 is not greater than eta 1, the obvious option left is eta 2 is either less than or equal to eta 1. So this is the correct option, right? Now we can repeat the same discussion by using the same arguments, and now if we reverse R1 instead of R2, and we also claim that eta 1 is greater than eta 2, we will come up with the similar type of discussion, and this statement will also be incorrect, and hence we will have to claim that now eta 1 has to be less than or equal to eta 2. So this part is just the repetition of first part by replacing R2 by R1 and by claiming the exact opposite of this statement. Now for these two engines R1 and R2 which are reversible, we are simultaneously claiming that this equation is correct as well as this equation is correct. So eta 2 is less than or equal to eta 1 as well as eta 1 is less than or equal to eta 2. So if we combine these two equations, the only option we are left with is that eta 1 has to be equal to eta 2. So the efficiencies of two engines working between the same temperatures T1 and T2 are the same, and we can continue this discussion for any number of engines 1, 2, 3, 4 and so on. So the essence is that if we have a source at temperature T1 and a sink at temperature T2, and if we have a large number of engines which are all reversible, then all of these engines working between the same two temperatures will have same efficiency. This was the second part, and first part stated that if we have a source at T1 and a sink at T2, then if we have a Carnot engine with efficiency eta working between these two temperatures, then if we assume another irreversible engine working between the same two temperatures, this engine's efficiency eta dash will always be less than eta, the efficiency of Carnot engine, which was the essence of first part of this theorem. So this was regarding the Carnot theorem. Now let us shift our discussion to the absolute scale. Typically, the temperature scales used to measure the internal energy or the kinetic energy of the molecules inside the system are degree Celsius and degree Fahrenheit. But both of these scales are relative, that is, they depend upon the volumetric expansion of the substance used to measure the temperature. For example, typical thermometer may contain mercury or alcohol or any other suitable material which is capable of expansion under the supply of heat. But in this case, we see that the Carnot engine's efficiency does not depend upon the nature of working substance. So efficiency which is defined as 1 minus Q2 by Q1, which is also defined or proved later that it is equal to 1 minus T2 by T1, is clearly a function of T1 and T2 alone. It doesn't matter which working substance we choose for its operation. So let us use this fact to define an absolute scale of temperature which does not depend upon any material properties. So in order to begin with, we assume a heat engine working between the temperatures T1 and T2 having efficiency eta. So we see that eta, which is 1 minus Q2 by Q1, is equal to 1 minus T2 by T1. This part we have proved, but let us for the discussion say that this is function of some two temperatures theta 1 and theta 2. We do not know the exact form of the expression, but efficiency is going to be a function of the source temperature, say theta 1, and sink temperature theta 2. So this can be rearranged, or this 1 minus q2 by q1 equal to f of theta 1 comma theta 2 can be rearranged to have q1 by q2 is equal to 1 upon 1 minus f of theta 1 theta 2, and this new function, let us call it as capital F of theta 1 theta 2. So this q1 by q2 is some functional of theta 1 theta 2. This is a functional equation. Functional equation. Now this is true for the first engine. Now imagine another engine working between T2 and T3. Now for that engine, if this is Q1 and Q2, then this is Q2 and Q3. So for that engine we can write Q2 by Q3 as equal to f of theta 2 theta 3. Now let us skip the intermediate step and consider another engine working between T1 and T3. For that, we will have Q1 by Q3 equal to f of theta 1 comma theta 3. So these are the three important relations which we have with us. Now we can see easily that Q1 by Q3 can be written as Q1 by Q2 into Q2 by Q3. Now if we use these two equations, it says that it is f of theta 1 theta 2 into f of theta 2 theta 3. But if we look at the LHS, this is the LHS. So we have f of theta 1 theta 3 by seeing at this equation equal to f of theta 1 theta 2 into f of theta 2 theta 3. Now note that on the left hand side theta 2 does not appear. So LHS is not a function of theta 2. So we have to eliminate theta 2 on the right hand side as well. This can be done by, there is a theta 1, okay. By assuming that f of theta 1 theta 2 as is some phi of theta 1 by phi of theta 2, and f of theta 2 theta 3 as some phi of theta 2 upon phi of theta 3. So this is some new assumption. We are saying that this function relation can be expressed as ratio of two other functions. So f of theta 1 comma theta 3 is equal to phi of theta 1 by phi of theta 2 into phi of theta 2 by phi of theta 3. Now we see that this phi theta 2 dependence disappears and we get phi of theta 1 by phi of theta 3. Now this f of theta 1 theta 3 is nothing but q1 by q3, which is equal to phi of theta 1 upon phi of theta 3. Now A suitable function of theta 1 can be chosen as the numerator. Similarly, a suitable function of theta 3 can be chosen at the denominator. The simplest choice is to take the theta 1 temperature itself and theta 3 temperature itself as the function. Now, just to denote it in a different way, we write it as T1 by T3 instead of using theta. Now, this capital T represents the temperature in SI unit Kelvin. So, Q1 by Q3 ratio is now equal to T1 by T3. So, this is how we introduce the absolute scale of temperature with the help of the efficiency of Carnot engine. Thank you.